Batteries and electrolysis. Batteries are a kind of electrochemical cell. You can notice here it's all in one. There's an anode and a cathode section, and a paste, in this case of manganese dioxide and ammonium chloride and carbon, to allow the reaction to flow. In general, usually you have zinc, that is the anode, and this ammonium salt and manganese dioxide, which is the cathode, and that's the part that causes electrons to flow. Eventually, once the cell has reached equilibrium, the battery is dead and you would throw it out. Here's another kind of battery, a mercury battery. Again, different component parts, and this is called a silver cell. This particular kind of cell has a zinc anode and a cathode that employs silver oxide as the oxidizing agent in a basic environment. The idea again is that the reaction is continuous until it no longer will run at equilibrium and the battery is dead. Batteries and galvanic cells are similar in that they are reactions that are spontaneous. Electrolysis is a little bit different. Electrolysis are reactions that do not occur naturally. In other words, delta G is positive for these kinds of reaction, and E cell is negative. These reactions don't occur spontaneously, but remember, just because a reaction doesn't occur spontaneously doesn't mean it doesn't occur. The way electrolysis works is electric current is forced through the cell to produce a chemical change for which the cell potential normally is negative and allows the reaction to occur. We did electrolysis back in Intro Chem at Parents' Day when we broke water into hydrogen and oxygen. We forced that to happen by putting the current through and breaking it into its component parts. The most common kind of question you're going to see is one that involves stoichiometry of electrolysis. Usually there's going to be some discussion of charge. So how much chemical change occurs with the flow of a given current for a specific time. If you apply the current for longer, more electrolysis will happen, and then more grams and more moles of product can be produced. So this relationship is going to be an important one. In other words, if you have current and time, you can get the quantity of charge. From that, you get the moles of electrons. From that, you get the moles of analyte, which is usually the metal, and then the grams of the metal or analyte. You can go in this direction, or you can go backwards. In other words, from grams to moles to moles of electrons, quantity, and then current and time. And again, from current and time to quantity of charge, you're going to use the information about coulombs. A coulomb is the number of amps times seconds. Quantity to moles, you're going to use the Faraday, which is the number 96,485. Because 1 Faraday, 1 coulomb is 1 mole of electrons. So let's look at an example where we have an unknown metal M and it's electrolyzed. Electrolyzed means that this reaction does not occur naturally and that you need electric current to force it to happen. It took 52.8 seconds for a current of 2 amps to plate 0.0719 grams of the metal from a solution containing MnO3. So the question is, what is the metal? What kind of metal is it? And this is one that I guess I would say is the backwards kind. How would we do this? Well, we want to figure out what the substance is. So I'm going to go backwards from what I said before. And let me get the correct pen to show you how to do it. So you're going to start with the time, and you're going to go to the coulomb of charge, then your mole of electrons, to your moles of substance M, to your your identity of M. In other words, you need to find the molar mass. All right, so we have an unknown metal, and let's see what are we going to say about time. Remember, Coulomb is the number of amps times seconds. For an amp is a Coulomb second. Either way, we're solving for coulombs. So we know that it took 2.00 amps times 52.8 seconds. That, of course, gives us 105.6 coulombs that have passed. Now, we know that 1 mole of electrons equals 1 Faraday, which remembers that 96,485. So if I have 105.6 coulombs, and I know that there are 96,485 coulombs in 1 mole of electrons, that means that 0.001 Faraday has passed, which equals 0.001 moles of electrons that have passed. In this particular metal, the metal, you can see, is a +3 charge. Because it's a +3 charge, if there's 0.001 moles for 1 electron, there's going to be 3 times as many, or 1/3 actually, moles of M. So we have 0.001 moles of electrons. Remember, in 3 moles of electrons, there's 1 mole of the metal M, which gives us 3.65 times 10 to the -4 moles of M. To calculate the molar mass, remember that's the number of grams per mole. We're almost to the end. You have the number of grams from the original, which is 0.0719 grams, and the moles we just calculated, 3.65 times 10 to the -4, works out to be about 196 grams. That's what you look up in the periodic table, find its molar mass, and hopefully you will find that the answer you can see under here is gold. Let's look at this piece of information. Consider a solution containing 0.1 molar of each of the following: lead ions, copper ions, tin, nickel, and zinc. And the question says, predict the order in which the metals plate out as the voltage is turned up from 0. So we want to see how long it takes, or which metal is going to come out of solution first. What we should do is we should look up the standard reduction potential information. And when we do, we can notice for lead, it's -0.13 volts. For copper, it's 0.16 volts. For tin, it's -0.14. Nickel, -0.23. And zinc is -0.76 volts. So, how can we figure out which one is going to plate out? It's the one that is least negative. The most positive one is going to plate out first. And that's why usually if you do a lab in AP and you're going to plate something out on top of something else, you're going to choose something that plates out relatively quickly and easily. So it's going to be copper, because that's the largest number. Whoops. Lead, tin, nickel, and then zinc, which is the lowest number there. And in fact, in the lab that we traditionally do, you will be plating copper on top of a brass key. The question next says, do the metals form on the cathode or on the anode? The cathode is where metals form. They always form because the electrons move from the anode to the cathode. So the cathode is where the extra metal is always deposited. Alright, here's a picture. This will look similar to what you will be doing. We will not be using a spoon, however. And since the metal forms on the cathode, electroplating can deposit metal on the spoon. So the anode is the metal, the solid metal that you would like to plate onto something else. So in this picture you can see that this spoon might be made of some cheaper material. Silver is pretty expensive. So if we take the silver ions and we can plate it out on the surface of the spoon, we have something that looks like silver on the outside, and certainly if it's durable enough it won't crack or chip or peel away. It appears like it's pure sterling silver or something like that, but actually it's what's called an overlay. It's metal on top of another kind of metal. You can buy inexpensive jewelry that way that can look silver or gold, and what has happened is sometimes it has been overlaid over some other metal. So that's the idea with electroplating. Again, these reactions do not occur naturally, and you need energy. Notice in this picture there's a power source. You need a power source to generate the electric current. With a galvanic cell, remember, those reactions are spontaneous. So that's probably the biggest difference in the two segments of the chapter. Galvanic cells are spontaneous, and electrolysis or electrolytic process, this is another word to say it, electrolytic processes are not spontaneous, and they need energy to